For 6 years, one question has haunted quantum computing. Is it real, or is it a magic trick waiting to be exposed? In 2019, Google claimed a breakthrough and watched it partially unravel under scrutiny. So when they made a new claim in 2025, the entire scientific community turned into skeptics, actively trying to prove them wrong. What happened next changed the conversation entirely. Let's go back to where this story really begins, because to understand why this moment matters, you have to understand the wound that never fully healed. In October of 2019, Google announced something that sounded almost like science fiction. They said their quantum processor, a chip called Sycamore, had performed a calculation in 200 seconds that would take the world's most powerful supercomputer roughly 10,000 years to complete. They called it quantum supremacy. Headlines exploded. Physicists celebrated. It felt like humanity had crossed into a new era of computation, one where the strange probabilistic rules of quantum mechanics could finally outrun the deterministic logic that had powered every computer since the digital age began. But the celebration didn't last. Researchers at IBM, one of Google's biggest rivals in the quantum race, pushed back almost immediately. They argued that with enough cleverness, a classical supercomputer could actually complete that same task in a matter of days, not 10,000 years. Later, other teams sharpened classical algorithms even further, chipping away at Google's advantage bit by bit. The gap that once looked like an unbridgeable canyon started to look more like a ditch that engineers could eventually fill in. The claim wasn't disproven exactly, but it was humbled. And in the world of science, being humbled in public leaves a mark. It taught the entire field a hard lesson, one that would define how every future claim of quantum advantage would be received. Extraordinary claims would need extraordinary proof, and more importantly, that proof would need to survive an all-out assault from the smartest skeptics on the planet. That lesson shaped everything that came next. For the following few years, Google didn't disappear from the quantum conversation, but it also didn't rush back to the microphone. Instead, its engineers went quiet in the way that serious scientists go quiet, which is to say they went to work. They weren't just trying to build a bigger chip. They were trying to solve the problem that had haunted quantum computing since its very conception, a problem so stubborn that some researchers had begun to wonder if it was even solvable at all. That problem was error. Here's the thing about quantum bits, or qubits, that makes them so maddening. Unlike the simple ones and zeros inside your laptop, qubits exist in fragile states that can be knocked out of alignment by almost anything. Heat, vibration, stray electromagnetic radiation, even cosmic rays passing through the Earth's atmosphere can introduce errors into a quantum calculation. And for decades, there was a nightmare scenario baked into the physics. As you added more qubits to do more powerful computations, you also added more opportunities for something to go wrong. More qubits meant more errors, not fewer. It was like building a taller tower out of blocks that got wobblier with every added layer. Many in the field feared this was simply the price of admission for quantum computing, an unavoidable tax keeping these machines fascinating laboratory curiosities rather than practical tools. Then, in December of 2024, Google broke that curse, unveiling a new processor named Willow, packed with 105 qubits arranged on a carefully engineered lattice. And the headline discovery wasn't just that Willow was fast. It was that Willow demonstrated something researchers had chased for almost 30 years. As they scaled up the number of qubits and applied more sophisticated error correction techniques, the error rate didn't climb. It dropped exponentially. For the first time, more qubits meant a more reliable system, not a less reliable one. This is the kind of result that sounds small on paper, but is enormous in practice, because it suggests that the road to large-scale, fault-tolerant quantum computers isn't just theoretically possible. It's actually walkable, one carefully engineered step at a time. Willow backed up that claim with a demonstration that echoed, quite deliberately, the spirit of the 2019 Sycamore experiment. Using a benchmark called random circuit sampling, Google's team showed that Willow could complete a specific, extraordinarily complex calculation in under 5 minutes. According to their estimates, the fastest classical supercomputer on the planet would need 10 septillion years to perform the same task. To put that number in perspective, that is a span of time so vast it dwarfs the age of the universe itself many times over. Julian Kelly, the director of quantum hardware at Google's quantum AI division, described error correction as the endgame for quantum computers, the technology that would finally let these machines take on very large problems and produce genuinely interesting, useful results. Naturally, the reaction to Willow's unveiling was a mixture of awe and, predictably, caution. Analysts pointed out that while the error correction breakthrough was real and significant, the random circuit sampling benchmark itself had no obvious real-world application. It was, in essence, a stress test designed to showcase raw computational muscle, not a tool for discovering new drugs or designing better batteries. Critics also noted that 105 physical qubits is still a long way from the 1,000 or more stable, logical qubits most experts believe will be required before quantum computers can tackle truly practical problems, the kind that would reshape medicine, materials science, and cybersecurity. Willow was undeniably a leap forward, but by Google's own admission, it was still a bridge, not a destination. So the world watched and waited to see what Google would do with this newly reliable hardware. Would they chase another headline-grabbing but practically useless benchmark, or try to build something that could survive the scrutiny that had wounded them back in 2019? The answer arrived roughly a year later, in October of 2025, with a level of caution and preparation that suggested Google's engineers had learned every lesson the hard way. What they unveiled was an algorithm called quantum echoes, and understanding why it matters requires understanding what makes it fundamentally different from everything that came before it. Random circuit sampling, the benchmark used in both the Sycamore and the original Willow demonstrations, produces a result that is essentially unverifiable in any conventional sense. You get a distribution of random outputs, and proving that a classical computer couldn't have generated something similar requires trusting complex theoretical arguments about computational complexity. It's convincing to experts, but it's also exactly the kind of claim that invites the sort of after-the-fact classical workaround that embarrassed Google back in 2019. Quantum Echoes was built from the ground up to avoid that trap. Instead of measuring something abstract and probabilistic, the algorithm measures a real physical phenomenon called an out-of-time order correlator, often abbreviated as an OTOC. Think of it like sending a pulse of sound into a canyon and listening for the echo that bounces back. In the quantum version, researchers take a complex quantum system, evolve it forward in time, introduce a tiny deliberate disturbance, a single perturbed qubit, and then run the entire process backward twice in a specific sequence designed to amplify the effects of that disturbance. The signal that comes back, the quantum echo, carries detailed information about how that initial disturbance spread and scrambled through the system. This isn't just a clever party trick. It connects directly to some of the deepest open questions in modern physics, including how information behaves near the event horizon of a black hole and how quantum chaos unfolds inside complex molecular systems. But for the purposes of this story, the most important thing about quantum echoes is that its results are deterministic and verifiable. Unlike a random sample of outputs, the numbers this algorithm produces can, in principle, be checked and reproduced by another sufficiently powerful quantum computer. That single feature transforms the nature of the claim. It's no longer just a demonstration of speed. It's an experiment other scientists can, at least theoretically, hold up to the light and confirm for themselves. And the numbers Google reported were staggering. Running the most demanding version of this experiment, Willow completed the calculation in roughly 2 hours. Google's researchers estimated that reproducing the same result using the best-known classical algorithms running on one of the most powerful supercomputers in existence, a machine called Frontier, would take approximately 3 years. In a related framing of the same result, Google described the quantum hardware as operating about 13,000 times faster than the best available classical approach. Some of the underlying calculations, if pushed to their full complexity, were estimated to require roughly 150 years of Frontier's computing time, compressed instead into a matter of days on Willow. Numbers like that tend to trigger an almost reflexive skepticism among scientists, and this time, Google seemed to expect it, even welcome it. Before publishing anything, the research team reportedly ran what amounts to an internal siege on their own results, actively searching for any classical algorithm, any clever mathematical shortcut, any tensor network trick that might allow a traditional computer to replicate the quantum echo's result in a reasonable amount of time. This kind of self-directed red teaming is rare in scientific publishing, but it makes sense given the history. If Google didn't stress test their own claim first, they knew the broader scientific community would do it for them, publicly and possibly embarrassingly. The result of that internal effort was published in the journal Nature, one of the most rigorously peer-reviewed publications in all of science, which added significant weight to the claim. The paper detailed how researchers explored multiple different classical simulation strategies, essentially trying every reasonable approach available to modern computer science, and found that all of them ran into what the team described as fundamental obstacles. The core issue lies in something called quantum interference. As a quantum system evolves and becomes more chaotic, the mathematical description of its state involves complex numbers, values with both a magnitude and a phase, that can constructively or destructively interfere with one another. Classical computers can simulate small versions of these systems with perfect accuracy, but as the system grows larger and the interference effects compound, classical algorithms either lose precision or require an amount of memory that becomes physically unmanageable, even for the world's largest data centers. This is the barrier the headline is talking about, and it's worth sitting with for a moment because it's genuinely profound. It's not that classical computers are simply slower at this task. It's that the fundamental architecture of classical computation, built on bits that are definitively either a 0 or a 1, cannot efficiently represent the layered, interfering possibilities that a quantum system naturally embodies. Trying to brute force your way through that complexity with a classical machine is like trying to describe a three-dimensional sculpture using only a single flat photograph. You can approximate it, you can gather more photographs from different angles, but at a certain point, the amount of information you'd need to fully capture becomes so enormous that the entire approach collapses under its own weight. But headlines love drama, and this is exactly where the story tends to get oversimplified or exaggerated. The phrase classical computing will never recover makes for a great thumbnail, but it doesn't quite capture what actual scientists in the field are saying. To understand the real picture, it helps to hear from people who weren't involved in Google's research and therefore have no reason to oversell it. R.M. Harrow, a quantum physicist at MIT who was not part of the Google team, offered one of the more measured and honest reactions circulating in the scientific press. He noted that it's pretty convincing that simulating this result classically would require some combination of a huge computing effort and algorithmic advances that nobody has come up with yet. But then he added something crucial. He said it's not crazy to imagine that those algorithmic advances could eventually be developed. In other words, even a leading expert who finds Google's result compelling is leaving the door open for classical computing to eventually catch up, at least partially, the same way it did after 2019. That historical pattern is exactly what keeps serious scientists cautious rather than triumphant. Peer reviewers who evaluated the Nature paper reportedly raised this point directly, reminding everyone that numerous previous claims of quantum advantage, including Google's own from 2019, have been narrowed or complicated as classical algorithms improved over time. Science doesn't move in straight lines toward a permanent verdict. It moves in a back-and-forth conversation, where one team makes a claim, another tries to poke holes in it, and the truth slowly emerges in that friction. Betting that this barrier will never fall, ever forever, isn't really how careful scientists talk. What they will say, and what genuinely is remarkable, is that right now, today, there is no known classical method that can replicate what Willow just did in any practical amount of time. There's also the matter of transparency, which has become an unavoidable thread in this story. Scott Aronson, a computer scientist whose voice carries significant weight in the quantum computing community, has been vocal about the challenges of independently verifying Google's claims. Without full access to the raw experimental data, outside researchers are limited in how thoroughly they can scrutinize the result themselves. Access to actual time on the Willow chip has also been limited, extended to select research partners, rather than opened broadly to the scientific community. This doesn't mean the result is wrong. It simply means the kind of open adversarial verification that gives science its credibility is still, in some ways, a work in progress here. Real confidence in a result like this tends to build slowly, through years of replication attempts, not a single announcement, no matter how impressive. And yet, even with all of that caution built in, something genuinely new happened with this experiment, something that goes beyond raw computational bragging rights. Google didn't just use quantum echoes to win an abstract benchmarking contest. They partnered with researchers, including a team connected to UC Berkeley, to apply the technique to a real scientific problem, functioning almost like a molecular ruler. Using organic molecules labeled with a specific carbon isotope, the researchers used the quantum echo measurements to predict the precise distances between hydrogen atoms within those molecules. Then critically, they verified those quantum-generated predictions against results from nuclear magnetic resonance spectroscopy, a well-established and trusted laboratory technique that chemists have relied on for decades. This step matters enormously because it moves the conversation away from pure computational theater and into applied usefulness. The quantum measurements didn't just match expectations. In certain cases, they revealed long-range atomic interactions, essentially invisible to classical modeling techniques, offering a level of geometric precision that could eventually refine our understanding of complex molecules, the kind involved in designing new pharmaceuticals, engineering next-generation batteries, or developing advanced materials. This is the difference between a magic trick and a genuinely useful instrument. A magic trick impresses you and then evaporates. An instrument gets used again and again, refined and improved, becoming a permanent part of how science gets done. Public reaction, as you might expect, ranged from genuine excitement to theatrical hype. Google's own leadership described the achievement using words like transformative, and prominent tech figures echoed that enthusiasm publicly, framing it as a signal that quantum computing was finally becoming relevant to the real world rather than remaining a distant theoretical promise. At the same time, more sober voices, including some embedded within Nature's own editorial commentary, pointed out the obvious caveat hovering over this entire field. Willow still lacks full, comprehensive error correction across all of its operations. And truly transformative, Industry reshaping applications will likely require something on the order of 1,000 or more logical qubits, each built from many physical qubits working together to suppress errors. Willow, brilliant as it is, remains a research platform, not yet a commercial engine capable of running the world-changing calculations that inspired this field in the first place. So where does that leave us, practically speaking, right now in the middle of 2026, looking back at everything that's unfolded since that Nature paper was published? The honest answer is that quantum computing has entered a noticeably different phase than the one it occupied even just a few years ago. The conversation used to center almost entirely on speed, on flashy comparisons between quantum processors and classical supercomputers, comparisons that often involve tasks with no real-world relevance whatsoever. Now, the conversation is shifting toward verifiability, toward reproducibility, and toward genuine scientific and commercial utility. Quantum Echoes represents a meaningful step in that direction, not because it definitively proves that classical computing has hit some permanent, unbreakable wall, but because it demonstrates, with real peer-reviewed evidence and a serious attempt at self-skepticism, that quantum hardware can now tackle problems that sit meaningfully beyond what today's best classical tools and algorithms can handle. There's an important distinction hiding inside that sentence, and it's worth pulling out into the light because it's easy to miss in the excitement. Today's best classical tools and algorithms is doing a lot of work in that phrase. Technology doesn't stand still, and computer science in particular has a long history of finding surprisingly elegant workarounds to problems that once seemed computationally impossible. The same community of researchers who narrowed Google's 2019 supremacy claim are almost certainly, right now, poring over the mathematics behind quantum echoes, looking for cracks, looking for shortcuts, looking for the kind of clever restructuring that turned an insurmountable 10,000-year classical calculation into something achievable in days. That's not a criticism of Google's work. It's simply how science functions at its best, a constant pressure test between opposing teams that ultimately produces more reliable, more trustworthy knowledge for everyone. What makes this particular chapter of the story so compelling is the deliberate way Google seemed to prepare for that pressure test in advance, rather than being caught off guard by it after the fact. By choosing a verifiable algorithm instead of a purely statistical one, by publishing through the demanding peer review process required by Nature, and by actively hunting for classical counterarguments before publication rather than after, the team behind Willow appears to have absorbed the central lesson of 2019 completely. Confidence in a scientific claim isn't built by shouting the loudest. It's built by surviving the most rigorous scrutiny available and by structuring your claim so that scrutiny is even possible in the first place. Still, the practical implications of all this remain for the vast majority of people, somewhere out on the horizon rather than sitting on their desks. This isn't a technology you'll be using on your phone next year, or even in the next several years. The systems involved require extreme cooling, delicate calibration, and highly specialized facilities, like the dedicated fabrication plant in Santa Barbara where these chips are actually produced. What Quantum Echoes and the broader Willow project represent isn't an immediate consumer revolution. It's a foundational proof, a demonstration that the underlying physics and engineering can be pushed into a regime that classical computers simply cannot follow, at least not with any method known today. And foundational proofs like that tend to be the quiet, unglamorous seeds from which entire future industries eventually grow, often taking a decade or more to fully mature into the tools we interact with directly. If there's a broader lesson buried inside this entire saga, spanning from that ambitious 2019 announcement through the humbling response from IBM through years of quiet engineering work, and finally arriving at this verified, peer-reviewed 2025 result, it might be this. Genuine scientific progress rarely arrives in the form of a single, dramatic, unchallengeable victory. It arrives in layers, through claims that get tested, partially walked back, refined, and then tested again, each round producing a slightly more solid foundation than the one before it. Google's Willow chip and its Quantum Echoes algorithm represent, right now, the most solid foundation quantum computing has managed to build. Whether classical computing truly never recovers from this particular barrier, as the more sensational headlines like to claim, is a question that only time, and an army of skeptical researchers determined to prove Google wrong, will ultimately be able to answer. But for the first time in a long time, the burden of proof has genuinely, meaningfully shifted. And that alone marks this moment as one worth paying very close attention to. It's also worth remembering that Google isn't racing in an empty stadium. Other companies and research groups have been chasing their own versions of this milestone, using entirely different hardware approaches, and their progress adds useful context to how significant Willow's result really is. IBM, the same company whose researchers punched holes in the original 2019 supremacy claim, has continued building its own superconducting processors, and has been just as vocal about error correction, pursuing a roadmap built around modular, interconnected chips rather than a single monolithic device. Meanwhile, companies working with trapped ion technology, a fundamentally different way of encoding quantum information using individually controlled atoms, have made their own claims about low error rates and high-fidelity operations. Even photonic quantum computing, using particles of light instead of matter, has produced its own headline-grabbing demonstrations recently. This competitive landscape matters because Google's claim doesn't exist in isolation. It exists inside a broader ecosystem of researchers with every incentive, scientific and commercial, to either replicate Google's success or find the classical workaround that would undercut it entirely. That pressure is exactly the kind of scrutiny that gives a result like this its long-term credibility, because a claim that survives contact with rival laboratories chasing the same prize carries far more weight than one sitting unchallenged in a single company's press release. There's also a quieter, more human dimension to this story that rarely makes it into the headlines. Behind every one of these papers are years of unglamorous laboratory work, engineers calibrating microwave pulses with extraordinary precision, cryogenic specialists maintaining refrigeration systems colder than the depths of outer space, and software teams writing error correction code that has to run in real time as the quantum system operates. None of that generates a viral headline on its own. It's slow, iterative, often frustrating progress, involving far more failed experiments than successful ones. The dramatic milestones we hear about, Sycamore in 2019, the original Willow unveiling in 2024, and now quantum echoes in 2025, are really just the visible peaks of a much longer, largely invisible mountain range of research. Breakthroughs like this rarely appear overnight, and the gap between one headline and the next usually represents years of quiet, incremental effort that isn't dramatic enough to make the news on its own. Looking forward, researchers across the field seem to agree on roughly the same set of milestones that still need to be reached before quantum computing becomes a mainstream tool rather than a specialized research instrument. Error rates need to keep falling, ideally well below the fraction of a percent range that chips like Willow have already begun approaching. The number of stable, logical qubits needs to climb from the dozens researchers work with today into the thousands. Most experts believe are necessary for genuinely complex, commercially valuable problems. And perhaps most importantly, the kind of verifiable, peer-reviewed application demonstrated by the molecular ruler experiment needs to be repeated and diversified across other domains, from drug discovery to materials engineering to the optimization problems underpinning global logistics and finance. None of those milestones are guaranteed to arrive on any particular schedule, but the direction of travel appears remarkably consistent, pointing toward a future where these machines gradually earn their place alongside classical computers, rather than replacing them outright. The next few years will likely determine whether quantum echoes becomes a permanent landmark in the history of computing or simply another impressive chapter in an ongoing, unresolved race between two fundamentally different ways of processing information. Either way, the fact that this question is even being asked seriously by serious scientists using peer-reviewed, verifiable data tells you just how far this field has traveled since that first tentative claim back in 2019. Quantum computing spent years promising a future that always seemed to sit just out of reach. With Willow, and with the careful, deliberate way this latest claim was constructed and defended, that future finally feels a little less like a promise and a little more like a beginning.